looking at the case where the energy is zero, right? In which case, we're going to have this to be zero, so we can just ignore that. Same with this, if E is zero. And if E is zero, we know that psi 2 is going to be AX plus B. Now, part A of this question asks us to use the boundary conditions to find four equations relating the constants A and B to C and G. So let's do this first. And what are the four equations we're going to have? So we want the wave function to be continuous at x equals 0 and x equals L. We also want the derivative of the wave function, the first derivative of the wave function, to also be continuous at x equals 0 and x equals L. Right, this should give us our first equation. And at x equals 0, exponent of this will be equal to c times exponent of 0, which is equal to c. And psi 2 at x equals 0 is just going to be b. So our first equation is that b equals c. Let me just put this here. We're going to come back to this again. So the second equation we're going to get is this. Now, this is equal to AL plus B. And psi 3 is equal to G times exponential of this. So that implies AL plus B is equal to G times now this is our second equation. Now, yeah, I do want to mention that we are getting all of these equations from the requirement that the wave function be continuous and the derivative also be continuous at x equals 0 and x equals L. That's why we're getting these equations. Now, let's take the derivatives. The derivative of this is going to be A, right? Because we're psi 2 is ax plus b, so the derivative of this is simply going to be a constant. Now the derivative of psi 1 is going to be c times all of this part, c times 2m v0 over h bar. Times exponential of times 0. When x equals 0, the exponent is going to be 0, right? So exponent 0 is just going to be equal to 1. So this means we have c over h bar root 2mv0 equals a. And this is equation number 3. Now for the last equation, we have this. So we know that this is equal to a, that's a constant. And this is going to be equal to the derivative of this will be negative L. So this implies that A is equal to G exponential of minus L. And this is our equation number 4. So according to the first part of this question, we managed to derive the 4 equations, right? So now for the second part, we need to show that if C is greater than 0 or if C is less than 0, then the 4 equations are going to lead to a contradiction that G is both greater than 0 and less than 0, which doesn't make any sense. And that is exactly why C must be 0. So we need to show this. Now let's take a look at the different equations. It's going to be more of a verbal explanation. Let's see. Let's start with equation 1. Let's say C is positive, right? C is positive means B is also positive, right? So you have B is positive, L is a positive quantity. And okay, actually, C is positive. C is positive implies B is positive, right? Now let's actually figure out what is the deal with A, because A depends on C, right? So C is positive implies A is also positive because these quantities are positive, H bar is positive, so A must be positive. So if C is positive, A and B are both positive. So C is positive implies AL plus B is positive. So here you have the LHS positive. Now let's look at this. If we look at this, the exponent part is going to be positive, obviously. It's not going to be negative. And that would mean that G is positive, right? Based on equation 2, we get G is positive. Now, if we move to equation 4, we know A is positive. This term is positive. This term is also positive. But you have a negative here. That means G is negative, right? So if C is greater than 0, if C is positive, equations 1 and 3 imply that A is positive, B is positive, like C is anyway positive. That's what we started with. Now equation 2 implies G is positive, but equation 4 implies that G is negative. Now how can G be both positive and negative? So that's the contradiction that we're going to do. We can do a similar exercise with C being negative, right? So just think if C is negative, then B is negative and A is also negative, right? So you have A and B negative. So this part, the LHS here is going to be negative in equation 2. But this is positive, so that would mean G is negative, right? But when we move to equation 4, we see that A is negative. All of this is positive, but you have a negative sign, which means G is going to be positive. So you have a contradiction again. And what happens if C is less than 0 is that equation 4 has a contradiction. So whether C is greater than 0 or less than 0, you're going to have a contradiction with G, right? So the only right answer is that C is equal to 0. That's your only right answer. Now we need to show that in part C equals 0 gives a wave function of 0 everywhere. So E equals 0 is not an allowed value. So let's go back here. So if C is 0, obviously this will be 0 if C is equal to 0 because you're multiplying everything by C. C is equal to B, so B is going to be 0, right? So your wave function is going to be AX. But A is dependent on C. So if C is 0, it means A is 0, right? C equals 0, A equals 0, and B equals 0. So psi 2 is definitely going to be 0 because it's AX plus B that is going to be 0. These are both 0. Now psi 1 is going to be 0 because it's C times something and C is 0. Psi 1 is 0. Now what about psi 3? So we need to figure out what is the value of G. Now G depends on A. If A is 0, then none of these elements are 0. So G has to be 0. So the fact that A equals 0 implies G is 0 implies psi 3 is 0. So your wave function in regions 1, 2, and 3, psi 1, psi 2, psi 3 is 0. So that tells you that psi is 0 everywhere, which doesn't make any sense because you do have a particle and that has to be there somewhere. The wave function cannot be 0. So because of these absolute results, we can conclude that E equals 0 is not an allowed value for A.